Hello everyone. Let me start with a simple question. Can light actually push something? Well, it turns out it can, not by force we can feel, but by knocking electrons right out of a metal surface. This fascinating phenomenon is called the photoelectric effect. When light of a suitable frequency falls on a metal, electrons are emitted instantly from its surface. These emitted electrons are called photoelectrons, and the resulting current is known as the photoelectric current. This was one of the first experiments that showed light can behave like a stream of particles, each carrying a specific amount of energy. It connected electromagnetism with the emerging ideas of quantum physics, a true turning point in science. It all began in 1887 with Heinrich Hertz, the same scientist who proved Maxwell's electromagnetic waves existed. During one of his spark discharge experiments, Hertz noticed something strange. When ultraviolet light illuminated the metal plates, the sparks across the gap became stronger. That meant the UV light somehow helped electrons escape from the metal, making it easier for electricity to jump across. Hertz didn't realize it at that moment, but what he had observed was the very first sign of the photoelectric effect. A few years later, Wilhelm Hallwachs and Philipp Lenard took Hertz's mysterious finding and turned it into a systematic experiment. They placed two metal plates inside an evacuated glass tube. When ultraviolet light hit the emitter plate, an electric current immediately began to flow. Electrons were being knocked off the plate and collected by the other electrode. But as soon as the light was turned off, the current vanished. Instant reaction, instant stop. Even more interesting, Lenard noticed that if the light's frequency was too low, no electrons were emitted at all, no matter how bright or intense the light was. This meant the frequency, not the intensity, decided whether electrons could escape. That was totally unexpected for classical physics. Now, here's the key idea. Every metal has its own threshold frequency, represented by F. If the frequency of the incoming light is below F, no electrons are emitted, no matter how powerful the light is. This happens because electrons need a minimum energy to escape, and that energy is related to the frequency of light by the relation phi0 equals h times f0, where phi0 is the work function and h is Planck's constant. For metals like zinc and magnesium, only ultraviolet light with very short wavelength can trigger emission. But for alkali metals like sodium, potassium and cesium, even visible light can do the job. To study this effect carefully, scientists designed a special setup, the photoelectric tube. It's an evacuated quartz tube containing two plates, the emitter C, which releases electrons when illuminated, and the collector A, which attracts those electrons. A battery creates a potential difference between them, and a commutator allows the polarity to be reversed. A voltmeter measures the potential difference, and a micrometer measures the photocurrent, the flow of emitted electrons. Monochromatic light, meaning single frequency light, is passed through a quartz window to hit the emitter plate. So, what happens when we increase the brightness of light? Well, when intensity increases, more photons hit the surface per second, which means more electrons are emitted per second, resulting in a higher photocurrent. However, the energy of each photoelectron doesn't change because that depends only on the frequency of light, not its brightness. That's a major clue. Light intensity affects quantity of electrons, not their individual energy. Now, let's vary the frequency and collector voltage. When the light's frequency is below the threshold, no emission happens at all, even with intense light. But once it's above threshold, electrons are emitted instantly. There's absolutely no delay between light arrival and electron ejection. If we increase the collector's positive potential, more electrons are attracted and photocurrent rises, until all emitted electrons are collected. But when we apply a strong negative potential to the collector, it begins to repel electrons. At a specific negative potential, photocurrent becomes zero. This is the stopping potential, represented by V. Let's bring it all together. The photoelectric effect reveals something revolutionary. Light isn't just a continuous wave, it's made up of discrete energy packets called photons. Only photons with energy greater than the work function of the metal can release electrons. That's why frequency, not intensity, matters. These findings couldn't be explained by classical physics. They paved the way for Einstein's photoelectric equation, which we'll explore next.